In this video, we're going to talk about the beginnings of quantum mechanics. So, um, to illustrate the weirdness of quantum mechanics, there's no escaping it. Quantum mechanics is kind of weird. To illustrate the weirdness of quantum mechanics, I want you to imagine a system with which you're probably familiar, right? You have swung on a swing at some point. If you haven't, you've seen people doing it. And if we talk about this from an energy perspective, it's an oscillating system. Let me point that out. It goes back and forth, back and forth. And if we talk about this from energy, as you swing up or back up, you're going up either way. You gain a certain amount of potential energy, and you lose a certain amount of kinetic energy. So when you stop, if you go forward, you've got all potential. And then as you start to come back, that potential turns into kinetic. When you get down here to the bottom, you've got all kinetic and no potential. And then the reverse happens as you go up this way. Right? So at any given point, your energy, your total energy is some combination of kinetic plus potential. But the point is, if we're not letting energy leave the system, right? If this is a perfect system with no air resistance, no friction, then your energy is some value at any point. At every point, it always adds up to be the same thing. Whatever you started with is what you finish up with. But you could have started with a different amount, right? You could have moved yourself up just a little bit. Let me get a different color. And so instead of starting in this position, maybe you started in this position, or maybe you started in this position, or maybe you started in this position. So necessarily, I've got to draw in different lines, but of course, we know how the world works. I could have started in between the black and orange line, or in between this orange line. And with those lines, I could have started in between there. The point is, I could start with really any old energy that I want to, or at least that's what it seems like to us. I don't have to start at any one of these lines. I could start in between them. Okay, so I could change my energy by any amount that I wanted to, just by pulling myself back, or if I'm pushing a child, pulling the child back just a little bit. So we would say that any energy is allowed. I can start off with as much energy as I want to. It would be really, really, really strange if you went to a playground and you were only allowed to start off at one of these orange lines or the black line. You couldn't start in between. You couldn't even get to the point where you're in between. And you might try. You'd pull it back, but even as you're pulling back the swing, it doesn't move back smoothly. It goes from here to here in an instant, and then from here to here in an instant, and then from here to here in an instant, and it never actually passes through the spaces in between. It just starts either here or here or here or here. You would think that's really, really, really weird, right? Another example. How old are you today? Well, depending on how you might say, oh, I'm, 19 and 32 days, or 19 and 2 months. What if you couldn't be 19 and 2 months? What if you could be 19 and 20, but you could never be 19 and a half? You went directly from being 19 to 20. You would go, well, that's really weird. Right? It is really weird. And in the macroscopic world, a situation like this, where I can't start out wherever I want to, I have to go from here to this orange line, to this orange line, to this orange line, which means I would only have certain energies allowed. In the real world, in our macroscopic world, that seems really, really weird. But as it turns out, in the quantum mechanical world, the world of the very, very small, that's exactly how things work. You might have seen this already if you've been through a chemistry class, and you learned that energy shells of electrons, right? The amount of energy contained in any certain electron is quantized. It only has certain quantities available. If you haven't been through chemistry, that might be news to you. You're going to learn a lot about it in chemistry. for what we're talking about here, it turns out if you have a system like this kid on the swing, but if you shrink that system down to what we call a quantum harmonic oscillator, something really small, really small, we're talking about electrons and atomic levels, there are actually only certain amounts of energy available to it. A man named Max Planck figured out that for quantum mechanical oscillators, things that are analogous to this, just on a really small scale, the energy available to that system is characterized like this: n plus 1/2 hf. We'll talk about what this parentheses means. Let me first introduce you to h. You know what f is. F is the frequency, right? If this is going back and forth, that completes a certain amount of cycles per second. That's the frequency. We know what frequency is, but this you might not be aware of. This is a number called Planck's constant. It is a very small number. I'm going to round. It's got some more decimal points, so what I'm going to give you, 6.626 times 10 to the negative 34th. That's really small. Units are joules times seconds. Energy times time, joules seconds. Remember that frequency has units of hertz, but a hertz is a 1/seconds. And so when I multiply a joule seconds times a 1/seconds, the seconds get canceled, and I'm left with energy, right? Energy. To have units of energy on the left-hand side, which means on the right-hand side, I've got to have units of energy. So this is Planck's constant. This is the frequency of the system, but by far the most interesting thing about this is what's in parentheses. N plus 1/2. Well, what is n? N is a positive integer. N is equal to 0, 1, 2, 3, etc., etc. What this says then is that this particular system only has certain allowed energies. You can't just have any old energy in this system. If I plug in n is equal to 0, I get 1/2 times hf. I get 1/2 hf, where f is the frequency and h is Planck's constant. If I plug in 1, I get 1.5 in here, which means I can have 3/2 hf. If I plug in a 2, I get 5/2 in there. I can have 5/2 hf. I can never have 1/3 hf. That's not allowed. That seems really strange. That's like saying you can't pull this kid on the swing back to any position. You have to either go here, or to this orange line, or to this orange line, or to this orange line, but you can never be in between there. That's really strange, no matter how you slice it. But it turns out that on the microscopic scale, this is actually how the universe works. A really interesting feature of this is that you can never get to 0, right? The lowest end you have is 0, which means if you plug a 0 in here, you still have some energy. You can never have 0 energy in this system. One of the macroscopic upshots of this is that you can never actually get something down to the temperature of absolute 0. It can never have 0 energy. Some of you might have heard that in previous classes or in chemistry classes. This is an expression of that same principle. You can't have 0 energy microscopically. That's really, really interesting, because we would say you can have 0 energy for the kid on the swing, right? He's sitting still down here at the bottom. But microscopically, quantum mechanically, there's always some energy in this system. That's really, really, really strange. This is just one example of a quantum mechanical system. Of course, there are other systems besides oscillators, and they'll have different expressions, but I wanted you to see this one because it really illustrates the strangeness that we're going to be dealing with when we start talking about quantum mechanics. So one of the things we have to do is sort of take our mind and just clear it of presuppositions as much as we can. A lot of what we've been doing in physics to this point is somewhat intuitive. it's physics after all, especially in mechanics. When you're in physics 1, we talked about gravity and things falling. These are things we see all the time. Here, though, when we start talking about quantum mechanics, our intuition will often lead us astray. I'm not telling you not to listen to your intuition. I'm just telling you, if you have some physical intuition about a system, it's a little bit less reliable here than it is in the macroscopic world. So that's a harmonic oscillator. Like I said, there are other systems we're going to look at as we go on. But this is just to sort of prepare you for where we're going in quantum mechanics. And I guess the last thing I want to talk about is the word quantum. A quantum is a discrete amount of energy. Discrete meaning a certain amount, right? This is not as in they won't tell your secrets if you tell them that. That's a different spelling. Discrete as in a particular amount. And that's what you have here. We say that this is a discrete spectrum. You can't have just any old value. You can have this amount, this amount, this amount. This is the same, the root of this word is the same root that we get the word quantity, which is another way to think about it. You may have this quantity of energy, you may have this quantity of energy, you may have this quantity of energy. That's what quantum means. And so the very name of this thing relays the information that we're dealing with discrete amounts, discrete packets of energy, not only in this system, but in other systems. Like I said, the other systems will have different expressions, but the idea is going to be the same.